Okay, YouTube. So in this video, I'll be covering a practice problem that reviews everything that we learned in lecture 5. So to start off with, we have this differential equation dy dt equals negative t plus square root of t squared plus 4y, all that over 2. And we have these initial conditions, y of 2 equals negative 1. And with these initial conditions, whoever came up with this problem was able to figure out that these are solutions to this given these conditions. So the question is, where are these these specific solutions valid? And why do these two solutions not contradict the existence-uniqueness theorem? Or in other words, since there are two solutions, there are no unique solutions because there's two solutions. It's not unique. Unique requires only one solution, and that being the only solution to the problem. But since there's two, it's not unique. So why does it not contradict the existence-uniqueness theorem? Well, let me just draw the chart from earlier. So we have continuous. So then if f of x, not f of x, but if f equals yes and delta f, delta y is yes, then unique. You get a unique solution. If f is yes, delta f, y, no more than one solution. And then both equals no. Then the theorem is inconclusive and you get no information out of it. Okay, so where are y1 of t and y2 of t valid? Well, it's basically when f is a yes, because, well, this clearly falls into this scenario, more than one solution, so that would require that f is a yes, even though delta f, delta y is a no. But we don't have to figure out if delta f, delta y is a no, because we already know it's a no. We just have to make sure that f is a yes. So, or otherwise, if f is not a yes, then it would end up in inconclusive. And if we get an inconclusive, then we have no evidence that these solutions even exist, because we don't know if these solutions are valid because the theorem's inconclusive. So we just have to make sure f is a yes. So let's do this. So f of t and y is what's ever on the right side. So negative t plus square root t squared plus 4y over 2. Okay? So now we need to make sure that in order for f to be continuous and, well, exist, then whatever is in the square root has to be positive. So t squared plus 4y has to be equal to or greater than 0, in other words. And in the end note of the lecture, I covered why the 0 of a square root is continuous. I covered that. I believe it's because whatever is not in the domain doesn't count for anything in the continuity. It's just whatever values exist. So as long as the function is continuous at where it exists, then it can be continuous. It doesn't matter whatever's not in the domain. Okay, so t squared plus 4y is greater than or equal to 0. So then that means that y would have to be equal to or greater than negative t squared over 4. So that is where y1, y2, t are valid. So this is our solution to part A. So I'm just going to leave this up here for 2 seconds for you guys to just... Okay, anyways, now I'll cover part B. Part B. Why do the two solutions not contradict the existence-uniqueness theorem? Well, this chart pretty much covers it already, and I already said. So, in other words, why do the fact that there's two solutions, so that So because they're not unique, because you have two solutions, unique requires just one solution that is the only solution to the differential equation. So why is it that fact that there's two solutions here, why does that not contradict the existence-uniqueness theorem? Well, remember, it's pretty obvious that this case falls into the f equals yes, delta f, delta y, no. But why? Well, we have to prove that. So we have to prove that we already know that f is a yes. We know that f is a yes given these initial conditions, and I could show you why. So dy dt equals, f of ty equals, well, -2 plus square root 2 squared plus 4 -1 over 2. So that's, well, let's see, it's just -1. So f of t and y are continuous and it exists at that point. So works out. And remember, it's a 0 in the square root. And I covered why it's continuous at that point. Okay. On the other, so we triggered the f equals yes, so it must fall into one of these two categories. Now we have to find delta f, delta y, and prove that it's not continuous there. So let's do that. So we're differentiating only with respect to y. So this t term doesn't matter here. So we get 4 over 2 times square root of t squared plus 4y multiplied by 2, because we have the 2 on the bottom. So that would mean that we get 1 over square root of t squared plus 4y. Let me make sure I didn't make any algebra error. I don't think I made algebra errors. Okay, so then when t equals 2 and y equals -1, then we would get 1 over square root of 4 minus 4 dne. Because it's dne, it can't be continuous there, obviously, because there's no value. And therefore, delta f, delta y is a no. Therefore, there are more than one solutions. There are more than one solution, as per the existence-uniqueness theorem, because in order for the existence-uniqueness theorem to apply, it has to be, f has to be a yes, so f has to be continuous, and delta f, delta y has to be continuous. But because only f is continuous, then a unique solution isn't guaranteed, but rather you'll probably get more than one solution. And you could verify that by plugging both of these into here and using these boundary conditions. There isn't much more for this problem. So thank you for watching this video, and I'll see you in the next lecture.